In this video, we want to consider how BGP makes a path selection decision. It's different from something like OSPF that goes with the lowest metric if there are multiple paths to get to a destination. Instead, BGP is going to consider a collection of path attributes. And depending on what literature you read, you might see that there are a different number of possible path attributes. But for the exam and for the real world, I want you to know about 8 of those. And to help you remember them, I want you to remember the acrostic, "We love oranges," as oranges mean pure refreshment. The W in "we" reminding us of the W in wait. The L in love reminding us of the L in local preference, and so on, like you see in this table on screen. And you can think of these path attributes as a series of tiebreakers. We start at the top and look at wait. Let's say a router has 2 ways to get to a destination network, and those 2 network entries in the BGP topology table have different weights. In that case, BGP will prefer the path that has the highest weight. If weights are a tie, then we go to local preference. If that's a tie, we go to originate, and so on and so on. Let's talk about in detail what each of these path attributes are really talking about. Weight, for example, that is a Cisco-specific path attribute, and weight is a way for us to influence our router's outbound decision. Let's say that we're connecting from our autonomous system to a couple of other autonomous systems, maybe different service providers. And each of those autonomous systems, they're advertising their internet routing table into our router, at our site, in our autonomous system. And maybe we have a faster link going to one of those service providers. And let's say we want to influence our router to use that faster link when going out to the internet. And unlike OSPF or EIGRP, BGP does not care anything about the bandwidth of a link. So if we want to care about that bandwidth, maybe we could do something like adjusting the weight to a higher value for a path that we prefer. Maybe we give routes learned over that preferred path a weight of 200. Routes over the non-preferred path, we give them a weight of 100. And we're going to prefer the routes that have the higher weight. And weight is locally significant. In other words, I'm not learning the weight from a neighboring router. I'm not telling neighboring routers about this weight. It's just something I can use internally to make my outbound decisions. It's almost like I'm taking a rubber stamp and I'm stamping a weight value on incoming routes, and I can use those values when selecting an outbound route. But if our weights are a tie, then we take a look at the local preference. And this is somewhat similar to weight. It can also be used to influence outbound routing decisions. However, it is not Cisco proprietary, and instead of keeping this information all to ourselves, the local preference assigned to a route, that's communicated throughout our autonomous system. And like weight, a higher value is preferred. And in our scenario where we had a faster link going to one ISP, we might mark routes coming in from that ISP with a value of 200 and mark routes coming in from the other ISP, the slower ISP, with a value of 100. And then when we need to make an outbound decision, we could select the route that has the higher local preference. But let's say that weight was a tie, so we looked at local preference. Local preference is also a tie. Then we go to the originate path attribute. And in just a moment, I'll show you the BGP topology table, and I'll show you exactly what originate means. But basically, the originate option says, where's this network connected? Where is it sourced from? We're asking, are we connected to it? Is it coming from us? If we are the next hop, then that is the route that I'm going to prefer. I prefer routes that I'm directly connected to versus routes I learned from another router. But maybe we're not the next hop for a particular route. We've got another tie. What's the tiebreaker now? It's the AS, or the autonomous system path length. And this is a lot like hop count you might see in the old RIP routing protocol. Not where we're counting the number of router hops, but we're counting the number of autonomous system hops. Let's say to get to a network via one path, I've got to go through 5 autonomous systems and then into the final autonomous system. Another path, I only have to go through 2 autonomous systems, and then I go into the final autonomous system. Well, I'm going to go with the one that has the shorter AS path. It has the fewest number of autonomous system hops. And this really goes back to us talking about BGP being a path vector routing protocol. We could see the path that we're taking. This is what we're looking at. We're looking at the autonomous system path. Which autonomous systems do I have to transit through? And then what is that final autonomous system containing my destination network? But what if AS path length is also a tie? Then we take a look at origin type. And origin type says, okay, how did this route get injected into the BGP routing process? Was it using the network command? Was it using a different routing protocol called EGP? And I need to inject a little history lesson here. When we say EGP, we're not talking about an exterior gateway protocol. We're talking about years and years ago, there actually was an exterior gateway protocol named EGP. And you might have seen that in the early 1990s as being a possibility to configure on a Cisco router. you could actually configure that protocol named EGP. Well, if a route got injected into our BGP routing table by the EGP routing protocol, then our origin type would be an E. If a network got injected into our BGP routing table using the network command, as it often is, then the origin type would be an I. And another way that a network could end up in our BGP routing table is if it were redistributed from another routing protocol. Maybe OSPF was redistributed into BGP. In that case, our origin type would be a question mark. So we've got really two potential because you'll never see the E, but technically we've got three potential origin types, I, E, and question mark. And I is preferred to E, and E is preferred to question mark. So real world, we'll never see the E. What we're saying is a network learned by the network command is going to be preferred over a network learned via a redistribution. And if origin type is a tie, the next tiebreaker is called the MED, the multi-exit discriminator. And I think of this as the closest thing that BGP comes to having an actual metric. Remember, with weight and local preference, higher values were preferred. Well, with the MED, much like a metric in other routing protocols, a lower value is preferred. And manipulating the MED is a way for us to influence inbound path selection decisions. We could advertise the MED out to our BGP neighbors. As an example, let's say that we're dual homed to an ISP. We have two different connections going into the same internet service provider. Well, we could advertise different MEDs over different links going into that service provider, and the link with the lowest MED, that's the one that they would use to send traffic into us to reach the network that we're advertising to them. And what if the MED is a tie? Then we look at the PAS, path attribute. And here we're asking if a network was learned over an eBGP path, in other words, it came from another autonomous system, or was it learned over an iBGP path? Was it learned from a BGP router within our autonomous system? And an eBGP path, that's going to be preferred over an iBGP path. But if everything is a tie, we've got one final tiebreaker, and that is the router ID. And many times I've seen it come down to this, where we're looking at different ways to get to a destination network, and we're going to select the network that was advertised from a router with the lowest router ID. And you might be wondering, how do I determine what those 8 different path attributes are? Well, we can take a look at the BGP routing table or the BGP topology table by giving a command of show IP BGP. And here on screen, I've highlighted those 8 different path attributes that we see in this output. Now let's walk through our acrostic of We Love Oranges, as oranges mean pure refreshment. The W in we reminds us of the W in wait. And if you give this command of show IP BGP, you'll see a column where the weightings of different route entries are given. And if you have 2 different ways of getting to a network, you're going to go with the path that has the highest weight. If that's a tie, then remember we love, the L in love reminds us of the L in local preference. There's a column for that. And much like weight, if we've got 2 ways of getting to a destination network, we're going to prefer the path that has the highest local preference. If that's a tie, we love oranges. The O in oranges reminds us of the O in originate. In other words, where did this route originate? Are we the next hop? If we are the next hop, then the next hop address, like you see here on screen, is going to be 0.0.0.0. Now let's go back to our acrostic. We love oranges as AS. That's the autonomous system path. We prefer shorter paths, where we're looking at a listing of autonomous systems that we have to transit through, and the one on the far right, that's the autonomous system containing the destination network. Next up, we love oranges as oranges, and this can be a bit tricky because we have more than one O in our acrostic. We have 2 oranges, but we need to remember that that second O refers to the origin type. Remember that if it's an I, then that means that this route got injected into BGP because we gave the network statement. If it's an E, and it will never be an E, but that would mean that the route got injected using the EGP routing protocol. And if the origin type is a question mark, then it means the route was redistributed into BGP. Next up is the MED, the multi-exit discriminator. We love oranges as oranges mean. The M in mean reminds us of the M in MED, and the MED is actually found under the metric column. And unlike weight and local preference, where higher values were preferred, with the MED or the metric, lower values are preferred, and we might set a metric to advertise to our neighbors to influence inbound routing decisions. And if we still have a tie, we love oranges as oranges mean pure. The P in pure reminds us of the P in PAS. And here we're asking, did I learn this from an iBGP neighbor or an eBGP neighbor? And I'm going to prefer an eBGP neighbor. And you can see on screen that we have an I over towards the left-hand side of the output. That's what we would see if this route had been learned through an iBGP neighbor. And if it's learned from an eBGP neighbor, then there will be nothing there. There's not an E, it's just blank in that case. And the final tiebreaker is the router ID. We love oranges as oranges mean pure refreshment. The R in refreshment reminds us of the R in router ID. And as we're considering a couple of ways to get to a destination network, if everything is a type to this point, then we'll look at the router ID of the advertising router, and we're going to select the path going to the router with the lowest router ID. And that's a look at how BGP makes its path selection decisions.